Welcome to the series of videos about setting and changing map projections in QGIS and Saga GIS. And they're also open source, and we are looking at map projections specifically. I'm sure you've all had situations like this where you get data and it doesn't fit into your data set, it just doesn't fall in the right place. Most of that is due to projections or projection errors. We want to first, before we go into the map projections, I just want to show you a nice little tool where we can have a look at the effect of map projections on shape, at least on size, specifically the Mercator projection. You can find this application at thetruesize.com, and it's actually quite nice to play around with. So, how does it work? You can type in the block over there, you can type the name of a country, and the moment you start, it will be predictive typing. I want to choose Brazil, and it highlights Brazil, and what I can do now is I can actually drag it around. I can drag it around to the United States, and I can see that Brazil is bigger than the United States, although the United States looks bigger because it's further from the equator. We can choose another one. Let's look at the Democratic Republic of the Congo, because that's on the equator. And if we start dragging that around to, for instance, say Greenland, to compare that, you can see that it's in actual fact a bit bigger than Greenland. So although it looks tiny on the map, it's in actual fact quite big, and that's the effect of a map projection on, specifically in the Mercator projections case, the size. And there you can see the Democratic Republic of the Congo, even it's a little less than half the size of Australia. The other one we want to cut down to size, so to speak, is Russia, because Russia is the biggest country in the world. But is it really as big as it looks on the Mercator map? No, it's actually quite a bit smaller compared to the other countries. If you put it on the equator, it's not the size of it's not as small as the DRC, and it's not as small as Brazil either. The first open source resource we want to have a look at is Proj4. Now, Proj4 is a library for performing conversions between cartographic projections, specifically written for that. And at the moment, you can see that it was started by Gerald Evenden, but it's at the moment hosted by Epsg. So there's the whole pedigree where you can get hold of it. Note at the bottom there, proj4.org. That's the website, which we'll go back to a little bit later on. So let's have a look what Epsg is, because that's what's hosting Proj4 at the moment. It's an open source geospatial foundation, and there it explains what it does. It was created to support the open source development or collaborative development of open source software. And there you can read everything about where it was, why it was funded, how it is funded, why it was started, and what it does. What is important to us is the libraries that we want to use, and specifically GDAL and OGR. Those are the open source projection libraries that most open source software use. Now, GDAL, Geospatial Data Abstraction Library, used to be separated into GDAL and OGR, where GDAL was raster and OGR was vector. But you'll note there, January 2017, it's been unified into one library. You can find user-oriented documentation, if you want to use it in software, how to work with it, and how do you do calls to the library and get the results back. So let's go and have a look at Proj4, because that's the language of GDAL. And if you look what projections is defined in Proj 4, you'll see there's a lot of projections defined. Important for us is the transverse Mercator projection, and sometimes we might want to use the universal transverse Mercator projection, which is also there, and there's a lot more that you can use. If you want equal area projections, you can get that. If you want other projections, you can get them off there. There it defines, when you click on transverse Mercator projection, it defines the projection for you. There's the statement which we'll use to call it in the GDAL library. It just tells you what the projection is and a definition, and there you see an example of a Proj 4 calling statement using Proj 4 parameters to define the projection to the GDAL library. Now we'll have an in-depth look at those later on when we get into actually projecting and transforming coordinates in QGIS. There's the ellipse defined and just coordinates that need to be changed. If you're really into the mathematics, you can get the formulas, all the mathematical equations to project and the inverse of the projection. So let's have a look at Proj 4 parameters. Those are the parameters that you put into your calling statement, and most of the parameters you're going to find on this parameter list. Here you can see the datum, ellipse, axes. You can have a look through them. There's a lot of stuff in there in the parameters which we're not really going to use. 2WGS84 is important because that's your datum transformations. There's also an axis statement where you can specify the orientation of your axes. But that only works in a projection transformation. It doesn't work as a statement of a projection on its own. So let's look at the ellipses or the ellipsoids that are defined. And there you have a list of all the ellipsoids that is defined in Proj 4. Obviously WGS84 is there, and it gives the semi-major axis, and the RF is the reciprocal of the flattening. Our Clark 1880 sits there, again the semi-major axis and the reciprocal of the flattening. Right, the final resource we want to look at is the Epsg code that you can use for projections. Epsg stands for European Petroleum Survey Group, which is now defunct, and but each Epsg code defines a projection in Proj 4 language. So you go to Epsg codes, you'll see there's a lot of them, and each one of them defines a different projection. And if you look to the right on the bottom side, you'll see RPS hook 94, which is our datum, and our Gauss conform projections, LO 15, 17, 19, 21. If you go to the next page, you'll find LO 23, 25, 27 up to 33 included in there. So that's the Gauss conform projection on the RPS hook 94 datum. If we want the Cape datum, we can search for it. We can search for Cape in there, and you'll see everything with Cape coming up. The first one there is our Cape datum latitude and longitude, and then there's the UTM coordinates, and then the Gauss conform projection on the Cape datum. If we click on one like 22287, you can see it's LO27. It shows you where it's valid, and if you want to look what it looks like or what is the elements of the projection, you can click on that, and you'll see that it is that Clark 1880 is the datum, and it's a transverse Mercator projection, and it's got no false easting and no false northing, and the y-axis is west and the x-axis is east south.